Alright, hello, my name is Levin Milani. This is my partner, Casey Lavelle. This is our final project for advanced microcontrollers. So what we decided to go ahead and do is we decided to make a wireless microphone. So we'll go ahead and get our code started up here. While that's going, I'm going to explain a little bit about what's going on with the hardware here. So we have two MSP430 microcontrollers. This is our transmitter microcontroller, and this one right here is our receiver microcontroller. So our microphone is hooked up to our transmitter microcontroller. So what's going on is this microcontroller is reading the value coming out of the microphone, and it's using its analog to digital converter to convert that analog signal to a digital value. Then this microcontroller is sending that digital value out to this IR emitter right here. And then you can see right across from here, we have an IR receiver. So what's going on the receiver side of things, we have another MSP430 microcontroller. This microcontroller is reading the pin on this IR receiver, figuring out whether the bit is a 1 or a 0, then takes that data, sends it out to this DAC, or digital to analog converter. That analog signal then gets sent over this audio line and gets sent up to these speakers. Alright, so a brief overview of how our code is working. So what happens on the transmitter side is the first thing that we send is a 1 bit, and then we follow that up with the 10-bit ADC value that we read. So from most significant bit to least significant bit. Then once we send that ADC value, we then send another 1, and then we send the next ADC value. So what's happening on the receiver is the receiver is throwing a hardware interrupt when this TX is sending that first 1. So what we noticed was, as we were working through our code, our internal clocks on our two different microcontrollers are a little bit off and they drift a little bit. And so we'd get more and more bit errors throughout time. And so what this allows us to do is it allows us to sync up our transmitter and our receiver and make sure that we're going to be reading those bits at the correct time. So right here on this edge, we sync up our transmitter receiver, read in our 10-bit ADC value. We then delay a little bit. We send our digital value to our DAC over I2C right here. And then once again, we had to throw another hardware interrupt and then read in the next ADC value, 10-bit ADC value. All right, so I'm gonna go ahead and show a short demonstration here, how this works. Things set up there. All right, so first I'm just gonna go ahead and run our code. So the first thing you're gonna hear coming out of the speakers is just a bunch of crackles, a bunch of noise. So it's a bunch of noise. All right, so what we have going on here is this computer is outputting a 408 hertz signal. It's outputting it to this earbud right here. So what I'm gonna do is I'm gonna put that 408 hertz signal up to the speaker. You're gonna hear a particular sound, and then what I'm gonna do is I'm gonna kind of slide through the frequency spectrum from 408 hertz up to 574 hertz. And what's going to happen is at 574 hertz, you're going to notice it sounds very similar to 408 hertz. All right, so here we go. Put that up there, turn up the volume. Slide through the frequency spectrum. And just one last thing to show that this actually does work, I'm going to go ahead and I'm going to put my student ID here in between the IR receiver and the IR transmitter. So go ahead and turn up the sound again. So that shows that it actually does work. We're not lying to you. So we're going to talk a little bit about why The audio signal sounded so similar at 408 hertz, and why it sounded so similar at 408 hertz as it did to 574 hertz. So we did a little bit of math, figured out our sampling period using the oscilloscope here. From that we could figure out our sampling frequency. So our sampling frequency is about 166, which is shown here and here. And so if you do just a little bit more math, our sampling frequency is 166, the signal we're putting in is 408, and so you get these frequency components shown here, so 574, 740, and 906, and then as this negative spectrum starts moving this way, we get some lower frequency components like 90. So doing the same sort of thing for the 574 hertz signal. So once again, we have our sampling frequency at 166. If we add 574 to that, you notice you get 740. You know, if you keep doing that, you get 906. And so what you notice here is that we have a 740 hertz spectrum, or part of the spectrum that's similar, and this 906 hertz part of the spectrum that's similar. So essentially what happened is if we kept continuing this out, you'd notice that the spectrum for these two frequencies are actually the same. So you notice, you know, they share some content at 90. There'd be some frequency content in here which isn't shown. And then as you can see right here, they both have 740 and 900 hertz components to the signals. So that's why it sounded so similar. Alrighty, that's everything I have to share with you today.